So today we look at the confidence interval for the ratio of two population variances. I will repeat that. I'm opening my whiteboard. So today we are looking at confidence interval for the ratio of two population variances. Confidence interval for the ratio of two population variances. And for this particular confidence interval, we shall use the F distribution. We shall use the F distribution. So we need, let me just remind you of the areas in the F curve. We need to remind ourselves about the behavior of the F curve. So first and foremost, the F curve is skewed to the right. And we said that when we talk about F alpha, we said that alpha was referring to the area to the right. Now, if we want confidence intervals, then it means that there is a particular middle area. There is a middle area, and then the two areas on the extreme right and left should be of size alpha over 2 alpha over 2 So when we are looking for the F value, then the F value for the F value that gives us an area of alpha over 2 to the right is what I'm trying to draw or to depict. So considering the small area to the right whose magnitude is alpha over 2, then the F value we are looking for is F alpha over 2. F alpha over 2, where alpha is the level of significance. And to identify the F value, the left F value, then that F value will be F of 1 minus alpha over 2. F of 1 minus alpha over 2, because the area to the right of the f value, which is to the left f value, the left f value, to the left of that, we have an area of alpha over 2, and to the right of that f value, we have an area of 1 minus alpha over 2. Okay, there's a comment. Let me look at it first. Maybe people are not seeing my screen. Yeah, somebody's not seeing my screen. Stephanie Cherono. Are you still not seeing my screen? Because I think I'm sharing. Stephanie, just check again and let us know. We don't want to leave you out. So I'm waiting for your response, Stephanie. Oh, she still cannot. How many people cannot see the screen? Because maybe what I need to do is to unshare, then I share again. Then we see whether she can also see. Let me unshare, then I share again. I'm sharing again. So I need your response again. Check now. Okay, good. Now she can see. Okay, that's fine. Yeah, great, great. Thank you too. Thank you too. Okay. So let me just repeat what I said for her sake. I said that we're just reminding ourselves of how we usually read the F values. First, we know that we have a middle area, and then the small area to the right is of size alpha over 2, and the small area to the left is of size alpha over 2 also. So we need to get these two F values. One of the F values is the one which is to the right, another one is to the left. So if first of all, we look at the F value to the right, which I have underlined in red, then we know we are looking for F of alpha over 2, because the area to the right of that F value is alpha over 2. And if we want to get the F value of the second F value, which I am underlining right now, that F value, for us to get the value, we know the area to the right should be 1 minus alpha over 2. Why? Because the area to the left of the F value that I am pointing at, the area to its left is alpha over 2. So the area to its right will be 1 minus alpha over 2. So that was just a reminder on how we usually read the F values. Now, so going back to our confidence interval for the ratio of two population variances, I need to share, I have a slide on that. I have a slide on that. So let me look for it. So we're looking for the confidence interval for the ratio of two population variances, and it's still opening up. So now I can also see the formula that we shall use for getting the confidence interval for a ratio of two population variances. So you can see that the left value of the confidence interval is given by S of x squared, S subscript y squared, 1 over F alpha over 2. Of course, the F values usually have 2 degrees of freedom. So here, n minus 1, m minus 1. And then the right confidence interval value will be given by sx squared, sy squared, 1 over f, 1 minus alpha over 2 with degrees of freedom n minus 1 and m minus 1. So I'm just giving you maybe 1 second to look at the formula for the confidence interval. And then we can look at an example. We can therefore look at an example. So in our example, we want to consider dataset 7. We consider dataset 7, whereby we need to determine a 90% confidence interval for the ratio of the population variances. We need to determine a 90% confidence interval of the population variances. So we want to refer to dataset 7. Dataset 7. Where is mine? Okay, I've seen mine. Dataset 7. So in dataset 7, we have brands. We have two brands, brand X and brand Y. And we can see for brand X, the first data value is 2,288. The last one is 2,112. For brand Y, the first value is 2592. And so for brand X, we have 10 data values, and the same applies to brand Y data. They are 10-10 each. They are 10-10 each. So of course, first and foremost, we need to, as per the formula for confidence interval, we need to calculate sample variance due to brand X and sample variance due to brand Y. Then we need to know how to obtain our F values, bearing in mind that the confidence interval level is 90%. So now you are experts of calculating sample variance. So we really do not have to do that. So I will just give you the answer for you to verify later. So for brand X, the sample variance is 16,466. 466.49. And for brand Y, the sample variance will be obtained as sy squared is equal to 3986 7.73. So we have our sample variances, and now according to the formula, we need to get the F values. We need the F values. So I will just draw another diagram again. We need to get the F values. We know that our level, the confidence interval should be 90%. So the middle area is 0.90. And then 1 minus 0.90 is 0.1. So 0.1 divided by 2, 0.1 divided by 2 is 0.05, 0.05, and the same size applies to the left region. It will be of size 0.05. So to obtain the F value, which is to the right, then we need F 0.05, and the degrees of freedom are n minus 1, m minus 1. For brand X, okay, for both data sets, the sample sizes are 10, 10. So because they are 10, 10, then the degrees of freedom are 9, 9. So we need to look for F 0.05 with 99 degrees of freedom. So I need to open my table. What am I looking for? I'm looking for, yeah, the F table. The F table, please let me unshare. Then I will share again. Desktop. Okay. Let me share my screen. So my screen is presenting. So we were looking for F 0.05 with 99 degrees of freedom. If we look at the top row, we can see 1, 2, 9. If we look at the first column, we can see 8, then 9, then 10, then 11. Looking at the second column, we can see 0.100, 0.050, 0.025, 0.010, and 0.001. So we need to okay, so we should concentrate on 9 and 9. And when we are looking at 9 and 9, there is 9 below 8 on the left, and there is 9 at the extreme end at the top from the right. For the intersection, but we look for it where we have 0.05. So starting from 9 on the left, then I can see 0.100, then 0.05. This is where we are. We are moving, we see 5.12, and we go on until we see 3.18. Until we see 3.18. So f.05 with 99 degrees of freedom is equal to 3.18. And then how do we get f.95? 0.95? And why am I saying that it is f.95 with 99 degrees of freedom? I'm saying that it is f.95 with 99 degrees of freedom because 0.95 is equal to 1 minus 0.05. So the area to the right, if we subtract 0.05, is 0.95. So now we need to get f.95 with 99 degrees of freedom. But I think there's a formula I had given you which states, because we don't have f.95, the formula stated that we just get f.05 and we are supposed to interchange the degrees of freedom. Okay, what we have here is 99. So even if we interchange, it does not become so noticeable. But if the degrees of freedom were different, for example, if it was, let's say 97, if it was 97, then it means if I use that property, then we would be having f.05 with 9 degrees of freedom. So the red writing is just for explaining should the degrees of freedom have been different. But because for our case it's 9, even if we interchange, it doesn't come, so it's not so visible. So this is just 1 over 3.18. And of course, if we had read the F value for degrees of freedom 97, and then now we find that we need to read the degrees of freedom for 7 and 9, then obviously it means we must go back to the table to read with degrees of freedom 7, 9. But I'm not going back to the table because 9 is just the same as 9. So this value which we had obtained of 3.18 is the one I just substitute here. Sorry, I substitute where I have 1 over 3.18, and so our answer is 0.3145. 3145. So we have obtained the two F values, and so we can substitute. Okay, there is a question. Okay, 0.3145. Yeah, I know you guys are sharper than me, so someone already had the answer there. Great. It shows we are understanding. So now we can substitute in our formula for confidence interval. We have Sx squared, we have Sy squared, we have the F values, so we can substitute. And so if we substitute, we get our confidence interval being 16,466, 66.49. That is Sx squared over Sy squared, 398. 867.73, and then we need to multiply that by 1 over, let me just look at it again, 1 over F alpha over 2. F alpha over 2, which is 3.18. And then let me just write this 16,466.49 divide by 3986.73, and we multiply that by 1 over 0.33145. And so this will give us our confidence interval. And we shall find that our confidence interval is equal to 0.11299 up to 1.3132. And as I said before, then we can just state that we can be 90% confident that the ratio of the population variances lies between 0.1299 and 1.3132 and 1.3132. Okay, so we continue. So we are through with the topic on confidence intervals. Now we want to go to the next topic, significance tests. Significance tests. Significance tests. So I had said that we shall revisit the reading of the tables and so on. And so we shall do it under this topic. What I mean is, for us to compute our solutions, we still have to, my laptop just went black briefly. And then now my cursor is refusing to move. Oh, maybe I should. And I'm getting a warning signal. Let me close some of these. And what is this? Okay, let me just close some of them. Okay, so significance tests. Let's try to do this. Now, you know, sometimes you may find yourself in a situation where you need to make a statistical decision. You may find yourself having two alternatives, and you need to decide whether one of the alternatives is correct and the other one is wrong, or whether the second one is the one which is right and the first one is wrong. So we usually perform these computations under significance tests. So as an introduction, we may just say that in many experimental situations, the conclusion to be drawn is phrased as a choice between two conflicting theories or hypotheses. So either we may have two conflicting theories or two hypotheses. So sometimes a conclusion to be drawn is phrased as a choice between two conflicting theories or hypotheses. For example, deciding whether a new vaccine is effective or, okay, there is a query. Someone, Lual, wants me to repeat the sentence. I said that in many experimental situations, the conclusion to be drawn is phrased as a choice between two conflicting theories or hypotheses. And I was giving an example like deciding whether a new vaccine is effective or non-effective. So we cannot say that a vaccine is semi-effective. It is either effective or not effective. And this applies to our current time, when the vaccine for COVID is being developed. Now, let us just make a few definitions in order for us to understand a few terms that we need to use under this topic. So the first definition, statistical hypothesis. So what is a statistical hypothesis? It's a statement which may or may not be true. A statistical hypothesis is a statement which may or may not be true. For example, aspirin cures headaches. So that is a statement which may be true or it may not be true. Aspirin cures headaches. If we want to find out whether it is true, then we must have some people who have headache and some people who maybe don't have a headache, and we give them aspirin and we see what happens. So there are only two scenarios. Either aspirin cures headaches or it does not. And to make a conclusion, we must perform a statistical test. Another definition, null hypothesis. I need to write this. Null hypothesis. So what is a null hypothesis? And you know, null hypothesis is denoted by H0. I don't know why when I'm writing, then my screen is blinking. I really don't know why it is blinking. So the null hypothesis is denoted by H naught. So what is a null hypothesis? So the null hypothesis, which we usually denote by H naught, or anytime I just say H naught, then just know that I'm referring to the null hypothesis. So it's the hypothesis to be tested for, it's the hypothesis to be tested for possible rejection. It is the hypothesis to be tested for possible rejection. For example, H naught. Wow, this is very strange. When I just start writing like this, the screen is blinking. H naught such that mu equals mu naught. So this is our null hypothesis. We are saying that the population mu is equal to mu naught, where you know mu naught is a number. Mu naught is a constant, where mu naught is a constant. So for example, we are saying the mean weight is 60 kilograms. So that is a null hypothesis. And it is the hypothesis to be rejected. It is the hypothesis to be rejected. Now, we have another hypothesis, which is known as the alternative hypothesis. The alternative hypothesis. Alternative hypothesis. Alternative hypothesis. So we always have a null hypothesis, or sometimes in stats we usually say we have a null and its alternative hypothesis. And how is it denoted? The alternative hypothesis is denoted by H1. In some books you'll find that they denote it by HA, but I will just use H1. So what is the what does that mean? What is the alternative hypothesis all about? So it's the hypothesis which is complementary. It is the hypothesis which is complementary to the null. It's the hypothesis which is complementary to the null, or to the null hypothesis. Now, I know my laptop required a reboot after my antivirus was updated, and I don't know whether that's what's causing the problem. I cannot reboot now. We will just continue like that. Now, so we are talking about the alternative hypothesis. So can we get an example of that? So you know, to have an alternative hypothesis, first and foremost, there must be a null hypothesis. So if let's say our null, let me stop sharing my screen. I see whether that's blinking. I stop sharing, then I share again. I see whether that blinking will stop. So as I'm doing that, I can take attendance. Then I try to share. So it's beginning to present again. Okay, so I was saying that for us to have an alternative hypothesis, first there must be a null hypothesis. So I'm saying that if H naught is such, we denote that if H naught is such that mu is equal to mu naught, if H naught is such that mu equals mu naught, then you know we have three alternatives. If I say, for example, that your weight is 60 kilograms, in real life, okay, so maybe I'm just guessing. Maybe I'm just guessing someone's weight and I say their weight is 60 kilograms. But you know what can happen is that maybe their weight is less than 60 kilograms, or it can be equal, or it can be greater than 60 kilograms, or it may just not be equal to 60 kilograms. How do we denote that? As an alternative hypothesis. So if our null hypothesis is H naught is such that, then one of the alternatives is H1 such that the mean is not equal to, the mean is just not equal to mu naught. Someone can just say that, no, my weight is not equal to 60. Or another alternative can be mu is less than, what do I want to say? Yeah, mu may be less than mu naught. It's possible. Maybe the weight is less than 60. The other alternative, so it's not that we usually write all these three alternatives. We are usually given a story, then from the story, we will find that we will select only one of the alternatives. We don't usually write all of them when we are answering a question. But now I'm just giving the three possible alternatives. Should there be a statement like what we have for that null? Now, what we note about these alternatives, like now, if mu is greater than mu naught, let me show this using a diagram for our understanding. Suppose, you know, statisticians like the normal distribution because almost everything in life is normally distributed. So suppose the mean was mu naught. Now, if the mean is greater than mu naught, so maybe the mean, of course, if the mean is greater than mu naught, then the mean is to the right, It could be having a value of, let's just give it a value of mu1. Now, when the mean, I'm looking at the third alternative, mu greater than mu naught. And so that's why I've put mu1 to the right of mu naught. When we shall be conducting a test with this third alternative, then it will be called a right-tailed test. It will be a right-tailed test. Right-tailed test. It will be called a right-tailed test. Looking at the second alternative, which is stating that H1 is such that mu is less than mu naught. So maybe if the mean, let's call it mu2, and it is less than, of course it is to the left of mu naught, then this test will be called a left-tailed test. It is a left-tailed test. It is a left-tailed test. What about the first alternative, where we have mu is not equal to mu naught? You see, if mu is not equal to mu naught, then it's possible that the mean is greater than mu naught, and it is also possible that the mean is less than mu naught. So the cases of mu1 and mu2 are being handled together, because the mean could be greater than mu naught and it could be less than mu naught. And so how do we classify that test, or what do we call it? It is classified as a two-tailed test. It is classified as a two-tailed test. So the null is always definite, as in the mean or the variance or whatever a value is given. So for the null, we always have something is equal to something. But for the alternative that we shall write, which will be only one of the three alternatives that we have, it will only be one of the three alternatives. The alternative we shall write will depend on the story that we are given. And once we know what the alternative is, then we shall be knowing whether it is a two-tailed test, whether it is a left-tailed test, or whether it is a right-tailed test. Now, let's just look at a simple example so that we try to understand this concept just a little bit more. So, in the example, a company produces 454 gram bags. 454 gram bags. The company insists that the mean net weight, the company insists that the mean net weight of the bags is 454 grams. Is 454 grams. So we are supposed to determine the null hypothesis, the alternative hypothesis, and we should also classify the hypothesis test. We need to determine the null hypothesis, the alternative hypothesis, and we also need to classify the hypothesis test. So one thing, what we know first and foremost, we know that we are talking about the mean here. In that story, there is something to do with the mean. And we know that the null is always such that, okay, for this particular question, the mean should be equal to something. Let's go back to the example. So a company produces 454 gram bags. The company insists that the mean net weight. So the company is insisting that the mean net weight of the bags is 454. So you, as the statistician, you have identified what the null is, that the mean is 454. This is the assertion by the company, and it is the hypothesis to be tested for rejection. So this is what the company is claiming. But in real life, maybe you may take one of the bags and you weigh it. Maybe you'll find that the bag weighs 450 grams. And maybe you take another one and you weigh it, and you find it is weighing 460 grams. So if the assertion is that the mean is equal to this, then the alternative can only be that the mean is not equal to 454. So from the null, that is how we identify the alternative. So for this example, we've already obtained the null, we already have the alternative, and now we want to classify the hypothesis test. Of course, from what I just stated before, have not equal to, then we know that it is a two-tailed test. It is a two-tailed test because mu is not equal to 454. So I said that as a statistician, you have a null hypothesis which may be rejected or may not be rejected. And maybe you have a situation where you need to make a decision. So you just do not make a decision by just looking or by asking yourself how you feel about the question, and then you just say, I feel that the first one is right, the second one is wrong. No. As far as that statistics is concerned, you must do some calculations. Then from your calculations, that is when you can make a decision. And if you have listened to the language I have been using, at first I said that H naught is the hypothesis to be tested for rejection. And then as I was explaining, I said something like, it is possible to reject H naught or not to reject H naught. So we also usually say that we may reject H naught or we may fail to reject H naught. So this brings us, so what I'm trying to say is that we have to do some calculations, and then we end up saying that we are or we are failing to reject the null. And for us to make the decision of rejecting or failing to reject the null, our calculations must fall in some region. Our calculations must fall in some region. So this brings us to our the next subtopic, which is rejection and non-rejection regions. Rejection stroke non-rejection regions. rejection stroke non-rejection regions. So we need to identify where these rejection and non-rejection regions are. And we shall look at rejection stroke non-rejection regions for so our title is going on for two-tailed, for two-tailed, for two-tailed, left-tailed, two-tailed, left-tailed, and right-tailed tests. Two-tailed, left-tailed, and right-tailed tests. So we want to identify those rejection regions for two-tailed, left-tailed, and that is two-tailed, left-tailed, and right-tailed, not light, right-tailed tests. Kevin is asking. Okay, he wants a clarification as to why we cannot use left-tailed or right-tailed for the example that I considered about the 454 grams. Now, what happens is we need to understand the story. You see, in that story, we were not told that the mean net weight of the bags is greater than 454. If the question was a company produces 454-gram bags, the company insists that the mean net weight of the bags is greater than. If the story was saying that it is greater than, then the alternative would have been H1 is such that mu is greater than 454. And if the story was saying the company insists that the mean net weight of the bags is less than, then the alternative would have been H1 is such that mu is less than 454. Now, in the question, it is just that the company is insisting that the mean net weight is 454. But you see, if I say that I weigh 70 kilograms, that is just a statement. Maybe my weight is more than 70. Maybe my weight is less than 70. So if I just say that my weight is 70 kilograms, then from that statement, what I have just said, if my weight is more or less, what takes care of that? Not equal to takes care of that. But if I said that my weight is greater than, then instead of not equal to, we will have the greater than sign. And this will become more clear as we deal with questions where there are words which clearly tell us whether it's less than, increased, decreased, or just differs. So as we go along, it will become more and more clear. So I was looking at rejection stroke non-rejection regions for two-tailed, left-tailed, and right-tailed tests. And I want to present a slide here, which I will use for explanation. So let me unshare, then I look for it. and I share. I'm presenting my screen. So I will use the normal distribution to explain this concept. So if we look at this diagram, let me just expand it a little bit. It's for a two-tailed test. I said that for us to make a decision, we must perform some calculations. Then, depending on the calculations, then we can either reject H0 or we fail to reject H0. How do we decide whether to reject H0 or to fail to reject H0? Now, we have been talking about alpha over 2 with you. So alpha over 2, you're very conversant with it. For a two-tailed test, then we have the two areas, one to the left, another one to the right, both each of which has a magnitude of alpha over 2. So of course, along the horizontal line, we have the z-score values. Z-score values. So suppose we make some calculations and we find that the value we found falls in the rejection region. Now I'm looking at the rejection region on the right. Okay, there is a question, or I hope my screen is visible. What is the problem, Celeste? Celeste, can you hear me? Oh, Celeste is having a problem, yeah? He could not hear, and then maybe his network is not working, so it's like he had to leave. I don't know whether Celeste is coming back. Oh, great, he's back. Celeste, are you having a problem with the... Celeste, you're back. Are you able to hear? Good, now he can hear. Felix Otieno is laughing. Okay, Celeste is back, so we can continue. And Felix is very happy. Okay, so what I was saying is that let us say we calculate some values, as we shall be doing in the forthcoming lectures, and then the value that we calculate falls in the shaded area to the right. Of course, you can see that we are referring to that region as the rejection region. So if the value that we calculate falls in the rejection region to the right, or it falls in the rejection region to the left, and for it to fall in the rejection region to the left, it must have a negative value, then we shall reject H0. But if the value falls in the area which is not shaded, then we shall fail to reject H0. Now, you can see that I have written there critical values. I have written there critical values. What are critical values? These are the values of the, maybe before I dictate that, let me explain what they are. Now, remember, like we were getting the z-score values. So depending on the question that has been asked and the value that we shall read from the table. So a value we read from the table is the one which could be the critical value. What does the critical value do? It separates the rejection region from the non-rejection region. That is why you can see those dotted lines. Those two dotted lines are the ones which I am calling the critical values. So the value where the arrows are coming from, the values at that point, at those 2 points, because for this test, which is being referred to as a two-tailed test, there are 2 critical values. Then the critical values separate the rejection regions from the non-rejection regions. So what I wanted to say was that the critical values separate the rejection and non-rejection regions. And the critical value itself, for example, suppose one of the critical values was 1.64 and another critical value was minus 1.64. So those critical values themselves, they also form they are also part of the rejection region. It is important to note that. The critical value separates the rejection from the non-rejection regions, and also they form part of the rejection region. So I think now you have had time to maybe draw this diagram. So because this is a two-tailed test, then we have 2 rejection regions and we have 1 region which tells us to fail to reject H0. So the statistic that we shall calculate, which is referred to as the test statistic, is the one that may fall on any of the regions, and depending on where it falls, that's when we shall say, okay, because it has fallen in the rejection region, then we reject H0. Or we will say that, oh, because it has fallen in the non-rejection region, then we fail to reject H0. So this is for a two-tailed test. What happens for, it's not here. What happens for a left-tailed test? So this is how a left-tailed test rejection and non-rejection regions look like. So for the left-tailed test, you can see that we have only 1 critical value, which is shown by the shaded line. So this 1 critical value, to the left of the critical value, the rejection region is of size alpha. The rejection region is the one which is shaded. It is of size alpha. To the right of the critical value, we have the non-rejection region. And so, if our test statistic falls in the non-rejection region, then we shall fail to reject H naught. So this is how a left-tailed test rejection and non-rejection regions look like. So maybe I just give you 1 second, then I present the right-tailed tests rejection and non-rejection regions. Okay, so now let's look at right-tailed test rejection and non-rejection region. So for the right-tailed test, this is what we have. Now, the rejection region is to the right, the shaded region. It is of size alpha. The shaded line denotes where the critical value falls or lies. And then to the left of the critical value, we have the non-rejection region. So depending on the value that we get from the test statistic that we shall have calculated, then we will know whether to reject H naught or whether we will fail to reject H naught. So when we shall be doing our calculations, we shall be drawing these regions so that we try to understand the question better before we make our decision. Before we make a decision. So going back to our whiteboard, now we want to look at examples. In the first example, we want to perform a one mean, Z test. Z test, of course, when you see Z, you know that we shall use the standard normal. We want to perform the one mean Z test. So when do we usually perform the one mean Z test? So the one mean Z test is used to perform a hypothesis test. It is used to perform a hypothesis test for a population mean mu, for a population mean mu when sigma is known. It is used to perform a hypothesis test for a population mean mu when sigma is known. Now, our test statistic, Z is X bar minus mu over sigma over square root of n. And you know, by now, I think by now you know a lot of statistics. And we know that this Z statistic, which we were calling the Z score value, we know that it is normally distributed with mean 0 and variance 1. So we shall use the standard normal distribution. So the example that we're looking at is in the year 2000. In the year 2000, the mean retail price of some books, the mean retail price of some books was $51.46. Excuse me. Was $51.46. This year's retail prices, this year's retail prices for 40 randomly selected books, this year's retail prices for 40 randomly selected books are shown in dataset 8, are shown in dataset 8, 40 of them. So I'm also displaying my dataset. Dataset 8. So I can see 56.00, 53.71, and the last one is 42.65. So those are this year's retail prices for 40 randomly selected books. So the question is this: at 1% significance level, at 1% significance level, determine whether this year's mean retail price, determine whether this year's retail price of the books has increased, whether the price has increased from $51.46, from $51.46. Assume that the standard deviation, of the book prices is $7.61. $7.61. So this is the standard deviation, $7.61. That is sigma. Sigma is equal to $7.61. So now I said that the one mean Z test is used to perform a hypothesis test for a population mean mu when sigma is known. Now you can see that we have been given sigma as 7.61, and this is why we are performing a one mean Z test. We don't have to calculate it. So that's why we are performing a one mean Z test. Sigma is given. And we know what our test statistic is. What about the level of significance? The level of significance is 1%. That is alpha is equal to 0.01. Now, whenever we start answering a question on significance tests, or we also call it a test of hypothesis, whenever we want to answer such a question, first and foremost, we must know what our null and alternative hypotheses are. We must know what our null and alternative are. In order to identify the null hypothesis and the alternative hypothesis, let's go back to the question and we digest it. So the question is asking whether this year's mean price of the books has increased. Whether this year's mean price of the books has increased. So the alternative, for the alternative, we know that the word increased has come in. So mu is greater than some quantity. And what was the mean which was given? 51.46. So now you can see where we are using greater than. Why are we saying greater than? Because of the word increased. What is our null? Our null is that mu is equal to 51.46. The null is mu is equal to 51.46. The alternative, we need to check whether the prices of the books has increased. So because of the word increased, then we use the greater than sign. Now, so we already have our null and our alternative. Now we need to substitute in the test statistic. And what is the test statistic? It is this one which I am calling equation 1. That is the test stat. For us to substitute there, we need to calculate the mean, sample mean. Mu is given, sigma is given. We know the sample size. So we need to calculate x bar. We need to calculate x bar. What is x bar equal to? It is equal to, of course, to get x bar, we just add everything and divide by 40. So x bar is 54.89. Zero to 5 x bar. So we can now substitute in our test stat, and as we are substituting, this value that we are calculating can be called Z observed because we are calculating it from the given data values. So x bar is 54.89 0 to 5. So x bar minus mu, what is mu? 51.46 divided by sigma over square root of n. Sigma is 7.61 divided by square root of 40, because we have a sample of size 40, square root of n. square root. And we get an answer. Our answer is equal to 2.8508. So remember, we have called that answer Z observed, the one I have circled in a red box. That is the answer. 2.8508, we're calling it the Z observed. Why? Because we are getting that 2.8508 using the data values that were given. And why am I insisting on that? Because we also need to get Z critical. Remember, when I was showing you the rejection and the non-rejection regions, I said that there is a critical, that we have critical values which separate the rejection from the non-rejection regions. Now we need to identify Z critical. And how do we do that? Coming back to the null hypothesis, I'm looking at the null hypothesis. I know that this is, we need to classify the test. I think this is a right-tailed test because mu is greater than 51.46. So it is a right-tailed test. How does that look like? I know I'm normal, so I know we just have our bell-shaped curve as usual, and it is a right-tailed test. It is a right-tailed test, and the shaded area to the right, which is now our rejection region, of what magnitude is it? What is the size of that shaded area? The size of the shaded area is alpha. And what was alpha equal to? Alpha was given as 0.01. So that shaded area, which is actually our rejection region, has a size of 0.01. And obviously, if that shaded region has a size of 0.01, then the opposite side, which is not shaded, has a size of 0.99. It has a size of 0.99. Now, you can see why the standard normal now is coming in handy. We need to determine the critical value. This value, the value which is at the point which I am circling in black on the standard normal curve, we need to determine that value. It is the one which is the critical value. It is the one which I am calling Z critical. We need to determine Z critical. So for us to determine Z critical, we go back to our lovely tables. We go back to our lovely tables and we need to look for the Z score value, which gives us an area of 0.99. So remember, we shall be moving from minus infinity up to a point where the area should be 0.99. So let us go back to our standard normal. We need Z critical, which is a Z score value. The Z score value for an area of 0.99. What happened? How many things are opening up? I don't know what this one is. The second one. Okay. So this is the standard normal distribution. Standard normal. I said that. Let me go back to the whiteboard so that we are together. We are looking for the z-score value such that the area to the left is 0.99. For us to get that z-score value, we need to look inside the standard normal table. 0.99, I can see 0.990, 0.990, 0.990, 0.990. I can see 4 of them. What can I see to the left? I'm seeing 2.3. So it can be 2.31 or 2.32 or 2.33 or 2.34. So if you wrote any of those values, 2.31, 2.32, 2.33, or 2.34, you are correct. And if I was marking in the exam, then I'm supposed to have 4 different answers, but they should be very close. But most of the time, statisticians, we usually use 3 most of the time. So even if you read some books, you'll find that when they're looking for that area of 0.99, they just put 2.33 only. So that is what we usually do most of the time. So this Z critical value is 2.33. So the Z critical value which we were looking for below the Z observed is 2.33. And now we have 2 important values here. Z critical, which is 2.33, and Z observed, which is 2.8508. So the question is this. Okay, we know. So you know 2.33 is separating the rejection from the non-rejection regions. And now we have calculated our Z observed. So we need to find out where Z observed falls. Does it fall in the rejection region or does it fall in the non-rejection region? So let's go to the standard normal. Of course, 2.85 falls somewhere to the right of 2.33 because 2.85 is greater than 2.33. And obviously, we can see that it falls in the rejection region. It falls in the rejection region. So we write that 2.8508 falls in the rejection region. Falls in the rejection region. Of course, you write that in full. So we write that 2.8508 falls in the rejection region. So what? So we reject H naught. So we reject H naught. We reject H naught. And if we are rejecting H naught, what does that mean? It means that the test results are statistically significant. It means that because we have rejected H naught, it means that the test results are statistically significant at 1% level. They are the test results are statistically significant at 1% level. And then after noting that, so you see, what did we say? 2.8508 falls in the rejection region. So we reject H0, implying that the test results are statistically significant at 1% level. So what conclusion do we make? We conclude that the prices of the books has or have increased. The retail price of the books has increased, or the retail prices of the books have increased. Let us just look at H0 and H1. Looking at H0 and H1, H0 was saying that the mean was equal to 51.46, but H1 is that the mean is greater than 51.46. Okay, we have rejected H0. We have rejected it. If we have rejected H0, then the alternative is the one which is correct. So because we have rejected H0, that is why we are saying that the test results are statistically significant. And so what is the conclusion? The conclusion is actually what we said in the alternative. The conclusion is that the mean retail price of the books has increased. Okay, someone is asking a question. Oh, Dennis wants me to explain more about statistically significant at 1% level. You see, when we, like in this example, we have rejected H0. And because of rejecting H0, let me just see the next question. I don't know whether it's asking the same thing. Okay, so I will answer Odero after I answer Dennis first. So Dennis wants me to elaborate on why the test results are statistically significant at 1% level. The level of significance that was given was alpha is equal to 0.01. That was the level of significance. And we have done our calculations and we have found that we should reject H0. And so we state that the test results are statistically significant at 1% level. Why is it important to state that the results are statistically significant at 1% level? It's because if we had a different level of significance, maybe we would not reject H0. Suppose the level of significance was 10%. Maybe we will find that we do not reject H0. Suppose the level of significance was 0.005. Maybe we will find that we do not reject H0. So we are rejecting H0 because the level of significance is 1%. Maybe at a different level of significance, we may not reject H0. That's why it's important to state the level of significance. Okay, let me look at Odero's question. Okay, first and foremost, in statistics, we don't talk about acceptance region. We talk of rejection or non-rejection region. Why don't we talk about acceptance region? Because we know, remember, there is an element of error. The level of significance is a probability of type 1 error. Now, so let me now answer what he's asking what would the statement be if Z observed was in the non-rejection region? If suppose Z observed was 2, let me write that in red. Suppose Z observed was equal to 2. Obviously, 2 is in the non-rejection region. So if that was the case, then what would we say? We would say that 2 falls in the non-rejection region. So we fail to reject H naught. And so it implies the test results are not statistically significant at 1% level. And then we will make the conclusion that the prices of the books have not increased. Any more queries? Any more queries? So, any more queries? Queries?